Unit 11 Biochemical Engineering Principles, Kinetics and Process Design. It is an important topic for GAT-B because it connects biology with engineering concepts used in real industries. In this unit, we will study how biological processes are designed and controlled. Topics like reactors, kinetics, and transfer processes are very important for solving exam questions. This slide talks about preparation strategy. The main idea is to focus on concept-based learning instead of just memorizing facts. For GAT-B, regular practice of MCQs and previous year questions is very important. Understanding concepts clearly will help you solve tricky questions easily. Biochemical engineering means applying chemical engineering principles to biological systems. It combines microbiology, biochemistry, and transport processes. The goal is to improve production and scale processes from lab to industrial level. Biological systems are complex and sensitive, so conditions must be controlled carefully. A bioreactor is a vessel where biological reactions take place. It is designed and based on mass balance, energy balance, and reaction kinetics. The main equation is input minus output plus generation equals accumulation. Important factors include mixing, oxygen transfer, and heat removal. Ideal versus non-ideal bioreactors. In ideal reactors, conditions are uniform and predictable. For example, CSTR has performed mixing and PFR has smooth flow. But real reactors are non-ideal and show problems like dead zones and channeling. RTD is used to study how much the system deviates from ideal behavior. Multi-phase bioreactors. Many bioprocesses involve more than one phase, such as gas-liquid in aerobic fermentation or liquid-solid in immobilized systems. Examples include bubble column and airlift reactors. Oxygen transfer rate is very important because it directly affects cell growth. Mass transfer is movement of substance from high concentration to low concentration. It follows Fick's law. In bioprocessing, oxygen transfer is very important. The liquid film usually offers more resistance, so it becomes the limiting step. Heat transfer. Microorganisms produce heat during growth, so temperature must be controlled properly inside the reactor. If heat is not removed, it can damage enzymes and reduce yield. Cooling systems like jackets and coils are used to maintain proper temperature. Rheology is the study of how fluids flow. Some fluids have constant viscosity, while others change with force. Fermentation broths are usually non-Newtonian. This affects mixing and oxygen transfer, which are important for reactor performance. Aeration supplies oxygen, and agitation helps in mixing the contents of the reactor. Increasing mixing improves oxygen transfer, but too much agitation can damage cells, so a proper balance is required. Media formulation and optimization. Media is the nutrient solution used for growing microorganisms. It contains carbon sources like glucose, nitrogen sources like ammonia, and other nutrients like minerals and vitamins. There are two types of media, defined and complex. To improve production, media optimization is done using methods like OFAT and advanced technique like DOE and RSM to get maximum yield. Microbial growth kinetics. Microbial growth occurs in phases lag, log, stationary, and death phase. The log phase is the most active phase where cells divide rapidly. The monod equation explains how growth rate depends on substrate concentration. It is important for understanding and controlling bioprocesses in industrial systems. Sterilization of air and media. Sterilization is done to remove all microorganisms and avoid contamination. This is very important because contamination can spoil the entire processes. Common methods include heat sterilization, filtration, and radiation. Important terms like D value and Z value help in understanding how microorganisms respond to heat. In a batch process, all materials are added at the beginning and not input or output occurs during the process. It is a closed system. This method is simple and has less contamination risk, but productivity is lower. It is commonly used in processes like antibiotic production. In fed batch processes, nutrients are added gradually during the operation. This helps control the concentration of substrate inside the reactor. It prevents substrate inhibition and improves product yield. This method is widely used in industrial production, especially for recombinant proteins. In continuous processes, fresh medium is continuously added and culture is continuously removed. This keeps the system at steady stage. At steady state, growth rate equals dilution rate. This method gives high productivity but requires strict control to avoid contamination. Microbial reactors are chosen based on the type of organism and oxygen requirement. Common type includes stirred tank, airlift, and packed bed reactors. The stirred tank reactor is widely used due to efficient mixing. Airlift reactors are preferred when low shear stress is needed. Enzyme reactors used immobilized enzymes attached to a support. This allows reuse of enzymes and improves stability. Types include packed bed and membrane reactor. The main limitation is mass transfer resistance, which can reduce efficiency. Instrumentation and process control. Important parameters like pH, temperature, and dissolved oxygen are monitored in bioprocessing. These must be maintained for proper cell growth. Control systems like feedback control are used to adjust conditions automatically. Sensors help in real-time monitoring and improve accuracy. Solid-liquid separation. The step is used to separate biomass from the liquid after fermentation. It is an important part of downstream processing. Methods include filtration, centrifugation, and sedimentation. The efficiency depends on particle size and density differentiation. Liquid-liquid extraction is used to separate compounds based on their solubility in two different liquids. It is commonly used to recover products like Antibiotics. The key parameter is the partition coefficient, which shows how a substance distributes between two phases. Equipment like extraction columns and mixer shuttles are used. Scale up means increasing the process from lab level to industrial level. During this, parameters like mixing and oxygen transfer must be maintained. There are challenges like heat removal and oxygen limitation. Economic analysis includes cost and feasibility to check if the process is profitable. In real systems, growth does not remain exponential forever. The logistic growth model explains how growth slows down when resources become limited. Factors like nutrient depletion and toxic products affect growth. This model helps in understanding real biological systems more accurately. In some cases, high substrate concentration reduces growth instead of increasing it. This is called substrate inhibition. It is explained by the Haldane model. This concept is important in systems like wastewater treatment and is often asked in exams. In product inhibition, the accumulation of product reduces microbial growth. This is common in processes like ethanol fermentation. As product concentration increases, growth decreases and yield is affected. This can be lead to early stationary phase. Oxygen transfer is very important in aerobic fermentation. The parameter KLa shows how efficiently oxygen is transferred into the liquid. It depends on agitation and aeration. Increasing these improves oxygen transfer, but too much can damage cells due to shear stress. Mixing time is the time required to make the system uniform. It is important for proper reactor performance. During scale-up, methods like constant power per volume or tip speed are used. There is always a balance between good mixing and cell safety. Optimization is done to improve yield and efficiency. Traditional methods like OFAT are simple but less effective. Modern methods like DOE and RSM allow studying multiple factors together. These methods save time and give better results. Yield shows how much product is formed from substrate. Productivity shows how fast the product is formed. These two are different, and this is a common exam trap. A system can have high yield but low productivity, so both should be understood clearly. Downstream processing includes steps like separation and purification of the product. It is a very important stage after fermentation. It includes techniques like filtration and chromatography. This stage can contribute up to 70% of total process cost. Bioprocess economics deals with cost and profit of a process. Costs are divided into fixed cost and variable cost. Break-even analysis is used to check profitability. The goal is to maximize output while keeping cost under control. For GAT-B, important topics include kinetics, oxygen transfer, and process types. These are commonly asked in exams. Common mistakes include confusion between growth rate and dilution rate, and yield versus productivity. practice helps avoid these errors. Subscribe BioBrainzz and stay updated with the latest GAT-B 2026 preparation tips.